we have defined the energy of a system, and we have said that that energy, total energy of the system, basically comprises of various forms. That is the macroscopic form and the microscopic form. And macroscopic form, we discussed that it comprises of the kinetic and potential energy of the system, and the microscopic energy is basically the internal energy of the system, and there are various components of internal energy that makes up the microscopic
सर ये
energy of the
आपकी
system. So
स्लाइड
together,
शो हो रहा है या ये ब्लैंक है?
no, it's blank at the moment. I'm just giving you an overview of what we have covered, and then I'll begin with the session. All right.
ठीक है सर.
So the total energy of a system, as I've already mentioned, comprises of two components: the macroscopic part, which is the kinetic and potential energy of the system, and the microscopic part that comprises the internal energy of the system. So that's the total energy of a system. And then other than that, you have energy interactions taking place with the system that you have defined. These interactions could be in the form of heat transfer. And we discussed that heat transfer is basically associated with the temperature difference between the system and the surroundings. So if there is any temperature difference between the system and the surroundings, and your system is not insulated, there would be a heat transfer that would taking place. That's one sort of energy interaction. If the system is adiabatic, then there would not be any heat transfer that would take place as an energy interaction form. Other forms of energy interaction, we said, are based on work, and there were different kinds of works that we had seen. There was electrical work, shaft work, spring work. So those kind of energy interactions fall in the category of work. And the third is basically associated with energy flowing into the system, or for flowing, oh sorry, mass flowing into the system and mass flowing out of the system. That's the third kind of energy interaction. Now, what we are trying to do in today's lecture is we are trying to correlate the energy interactions and energy of a system to develop a energy balance equation. So the basis of this energy interaction equation would essentially be the first law of thermodynamics. And what does the first law say? It says that it's the principle of conservation of energy, and there are various forms of energy interaction, various forms of energies that you've already seen: kinetic, potential, internal energy, and internal energy is further divided into subcategories, and there are energy interactions. So based on this first law, we'll try to develop an equation relating the energy and energy interactions. As for the first law, the most common example is that energy cannot be, as it says, the energy cannot be created nor it can be destroyed during process. It can only change forms. How? You have a stone over here which has the potential energy of 10 kilojoules and kinetic energy of 0 kilojoules. This is at state 1. Now, if you release the state, the system, which is your stone, if you release this system, it would start coming down, and there would be a change in the potential energy and kinetic energy of the system at state 2, somewhere at a height of delta z. At this height, the potential energy is reduced to 7 kilojoules and the kinetic energy has increased to 3 kilojoules. So that means the total energy remains the same. It's the conversion of energies that is taking place for the total energy of the system. uh, is it clear so far?
Yes, sir.
All
Yes,
right.
sir.
All right, great. So let's say I define this condition as my state and this condition as my state 2. There are two states I'm talking about. Remember, whenever I'm talking about a state, let's say state 1, the energy at that state is fixed. Energy is related to the state. This energy is related to the state, and it is the total energy at state 1, which means energy is a state property. All right. Energy is a state property. Similarly, at state 2, you have a total energy of the system, which is again the property of the state. So unlike heat and work, heat has no meaning at state 1, heat has no meaning at state 2, but there is a meaning of energy at state 1 and state 2. That means there is certain amount of energy which is associated with state 1, and similarly there is certain amount of energy that is associated with state 2. uh, I'll we'll have, sorry, we'll have the statement in front of us which says, which is again about the first law, and it says for all adiabatic processes. That means those processes in which Q is zero, there is no heat transfer taking place. Then it says for all adiabatic processes between two specified states. That means I'm talking about state 1 and state 2 of a closed system. Closed system means that in this system there is no mass flowing into the system, so mass flow rate is zero. What kind of energy interactions can we have? Energy interactions could be in the form of Q, which is heat transfer. It could be in the form of W, which is the form of work, or it could be in the form of mass flow rate. So as per the statement that we have discussed so far, there is no Q and there is no mass flow rate taking place. For such a system, the net work done, the amount of work done on the system or by the system, the net work, whatever it is, whether you have done 20 kilojoules of work on the system and the system has done, let's say, 15 kilojoules of work. So the total work done is basically 5 kilojoules. It would remain same regardless of the nature of the closed system and the details of the process. This means that no matter how you perform a work on a system, if the system is closed, that means there is no mass flowing to the system and there is no energy interaction in terms of heat. The net work done would be same no matter how you do it. Is this point clear so far? Is the point clear so far?
सर ये डिटेल्स ऑफ द प्रोसेस का मतलब क्या है?
I'm coming to that. I'm coming to that. So far, you have, I mean, as far the statement is concerned, you have understood that we are talking about an adiabatic system. We are talking about two states, state one and state two. We are talking about a closed system, and we are saying the total amount of work done, which is the net work done, would remain same no matter how you perform the process. Uh, the meaning is clear. You just don't know the details of the process, what I'm talking about. Otherwise, the statement is clear.
Yes, sir.
So let's see what is meant by the details of the process. Let's say I have an adiabatic room. Adiabatic room means that the Q or heat transfer is zero. And I am talking about a closed container. That means mass flow rate is zero. So it's a system which can have energy interaction only in the form of work. Is it so?
Yes, sir.
All right.
Yeah.
So, all right. In this system, there is a shaft that is being placed, and there are rotors associated with the shaft. So, as the shaft is moving, work is done on the system, and the work done is 8 kilojoules. Clear? Is it clear?
Yes, sir.
Is the point clear?
Yes, sir. Clear.
All right. So, I am doing work on the system by rotating a shaft, which results in my system moving from state 1 to state 2. And as it moves from state 1 to state 2, the change in energy of the system is 8 kilojoules. All right.
Yes, sir.
Yes, sir.
So this is one way of doing work on the system where the amount of work done is in the form of shaft work and the energy change is equivalent to the amount of work that you have done on the system. If I perform this work by some other way, the same amount of work, regardless whether I'm using the shaft or whether I'm using a battery. That means if I'm, let's say, for example, the work in over here is 8 kilojoules. If the work that I am doing, the net work is 8 kilojoules, the change in energy of the system would be what?
8 kilojoule.
8 kilojoules. So it means whether you are performing the work in the form of shaft, running the propeller, or you have attached a battery, or you have done some other work, or you have attached a bulb over here. If you are if you are providing the net work done that you are doing is 8 kilojoules, the change in energy of the system would essentially be 8 kilojoules. So no matter how you do the work, the change in energy of the system as it moves from state 1 to state 2 would be equivalent to the net amount of work done on the system. Is this point clear?
Yes, sir.
So if you see over here, the details of the process means whether you are moving the shaft in the system, or you have placed a battery in the system, or you are lighting a bulb in the system, the net work done would determine the change in energy of the system as the system moves from two specified states. This means that energy at state 2, there would be some energy at state 2, there would be some energy at state 1. The difference in the energy of the two states would be equivalent to the net work done on such a system, regardless of how you have done it. Clear?
Yes, sir.
All right.
सर
Please.
सर ये सिर्फ एडियाबैटिक प्रोसेस के लिए होगा सिर्फ
No, for now, what you are trying to say is that the change in energy of the system, अगर आपका system state 1 से state 2 पे जा रहा है, state 1 it would have certain energy, state 2 it would have certain energy. The change in the energy of the system would be basically due to the energy interactions taking place. In a simpler case, you have seen that the only form of energy interactions is in the form of work. All right. So whatever the net work is being done on the system would result in the change in the energy of the system. It would get a little complicated. We'll see in the next example. So far, is it clear?
यस
सर
सर
इसका मतलब ये
Sorry.
कि
जी जी
एडियाबैटिक यानी ये सिस्टम क्लोज हो और हमारे पास हीट ट्रांसफर ना हो रहा हो
जी
क्या नाम सिस्टम और सराउंडिंग में, तो
जी
हमारे पास तब ये कंडीशन अप्लाई होगी.
नहीं, ये कह ये रहे हैं कि अगर हमने सिंपलर केस लिया, वी हैव टेकन अ सिंपलर केस इन व्हिच देयर इज ओनली वन फॉर्म ऑफ एनर्जी इंटरैक्शन टेकिंग प्लेस. दैट फॉर्म ऑफ एनर्जी इंटरैक्शन इज बेसिकली वर्क. ऑलराइट, सो फार क्लियर?
यस सर.
सो इन दैट फॉर्म, जहां पे आपके पास सिर्फ एनर्जी इंटरैक्शन वर्क की फॉर्म में हो रहा है, चेंज इन द एनर्जी ऑफ द सिस्टम जो होगी, it is not dependent upon how that work is being performed, whether it is being performed by moving a shaft or by placing a battery or by lighting a bulb. Whatever the form in which you are performing the work, the net work that is being done would result in the net change in the energy of the system, for a simpler case which is adiabatic and closed system. Clear?
Yes sir.
All right. Let's say we have a more complicated example. A complicated example is which example? Where you have, there is, the system is not adiabatic, there is heat flowing into the system and there is heat flowing out of the system. Clear?
Yes
So
sir.
now the system is not adiabatic, and fortunately enough, there is no work interaction taking place. So the change in energy of the system would be equivalent to the change or the net heat supplied to the system, which is 12 kilojoules. Clear enough?
Yes sir.
So again, a simpler case where you have
Yes, sir.
taken only the heat interaction. What it is trying to say is that change in energy of the system is only based on the energy interactions that the system is having with the surroundings. Clear?
Yes sir.
All right.
Yes, sir.
All right. Based on this, we develop the energy balance equation. Energy balance equation, what does it say? It says the net change, that means whether it could be increase or decrease in the total energy of the system during any process, is equal to the difference between the total energy entering into the system and total energy leaving the system during that process. Is this point clear?
Yes sir.
All right. So the equation is that total energy entering into a system, what are the mechanisms by which it could enter into a system? It could enter in the form of heat, it could enter in the form of work, it could enter in the form of mass. Similarly, it could leave the system in the form of heat, work, and mass. These are the energy interactions that can take place. So the total energy entering into the system minus total energy leaving the system would result in the change in the total energy of the system. These are the factors that would govern how the energy of the system changes. Clear?
Yes, sir.
All right. Moving on, if I have to write it in scripts, I would say E in, that means energy flowing into the system, minus E out equals to the change in energy of the system. We'll look at these two, these two sides of the equation, the E in minus E out and delta E system. We'll look into these forms separately. So we'll look into this side of the equation, and we'll also look into this side of the equation, how they are related and what components basically form these two sides. Again, it is in this example, you have an adiabatic process, so there is no heat coming in and going out. The system is closed system as represented by the dotted line. The only work done on the system is boundary work, which is done onto the system. So it is coming into the system, and this change would be essentially equivalent to the amount of work done on the system. A more complicated example, now you see that how is the energy changing? This energy is coming in the form of heat, this energy is going out in the form of heat, and this is the sharp work that is done in the form of work. So the total energy change of the system would be what is coming in is heat coming in as 15 kilojoules, plus what is coming in, work is coming in as 6 kilojoules, plus what is going out, 3 kilojoules of heat is going out. So the change in energy of the closed system would essentially be 18 kilojoules. Is this clear?
Yes, sir.
Yes.
All
Yes,
right.
sir.
All right. Good. So now we'll move and we'll see what is or how do we calculate the change in energy of the system? How is it that we assess the right hand side of the equation? If you remember, the total energy of a system is dependent upon what characteristics I had already given you an overview at the start of the presentation. What components make up the total energy of a system?
Sir, macroscopic,
Very
that
good.
is kinetic energy, kinetic.
Macroscopic and microscopic. Very good. So we'll see what macroscopic components are and what microscopic components are. So
Kinetic.
change means energy at the final state minus energy at the initial state. That means E2, which is the final state, minus E1. That is essentially the change in energy of the system. As I'd already mentioned, that at any state you would have energy as the property of the system. So far, is it clear? At state 2, you will have some energy, which is the total energy of the system. At state 1, you'll have the total energy, which is total energy of the system. And the difference of the two would give you the change in energy of the system. And what is the change comprised of? It is comprised of the change in the microscopic energy, which is the internal energy, and change in the macroscopic component of the system, which is the kinetic and potential energy changes. Is it clear?
Yes, sir.
Yes, sir.
All right. Moving on, if we look at these three components individually, what is meant by the three components individually? It means that the microscopic change is associated with change in internal energy, which is nothing but mass multiplied by specific internal energy change. That means mass multiplied by kilojoules per kg. That would give you the energy. Is it clear?
Yes, sir.
Is this form clear to you? That the total energy, which is in kilojoules, is essentially mass of the system multiplied by the change in specific internal energy of the system. Is it clear?
Yes, sir.
Kindly let me know if it is clear to you or not, so that I could move on.
Yes,
Yes,
sir.
All right. The kinetic energy is based on the velocities of the system at state 1 and state 2, and the potential energy is based on the elevation of the system at state 1 and state 2. For a stationary system, if the system is not moving with regards to an outside reference, and it is not having change in elevation, what would happen to kinetic and potential energy?
Zero change.
No change.
Kinetic energy zero, potential energy same रहेगी.
Very good. So for a stationary system, the change in energy of the system would essentially be equal to change in internal energy of a system. For a closed stationary system, the total change in the energy of the system would be essentially equivalent to the change in internal energy of the system. As it is mentioned over here, the total change would be equivalent to the change in internal energy of the system. So this is the right hand side of the equation. Now the values of internal energy at state 1 and state 2, you will see in the upcoming chapter, chapter 3, that you can find out these values from the table. If you know the state of your system, you can find out the internal energy at those states. All right. For example, if you know the pressure and specific volume at state 1, you can find out the internal energy at state 1. For a system of, let's say, air or nitrogen or another gas, you can find out the, if these two states are fixed, you can find out the internal energy at state 1. Similarly, if you have another state, you will have another pressure and specific volume, you can find out the value of internal energy at state 2 using the tables that are given to you. Clear?
Yes, sir.
All right. Moving on, now we'll look at the terms on the left hand side of the energy equation, which is energy in and energy out. And this energy in and energy out is basically related to the mechanisms of energy transfer. And what are the mechanisms of energy transfer? They are heat transfer, work transfer, and mass flow. So for an open system, you could have mass flowing into the system and mass flowing out of the system. You can have work done on the system and work done by the system. And similarly, you can have heat flowing into the system and heat flowing out of the system. So these are the energy interactions which deal with the left-hand side of the equation, that is energy in and energy out of the system. So if we develop the left-hand side of the equation, we see that E in minus E out is basically dependent upon heat in and heat out, work in and work out, and mass in and mass out. And that would be equivalent to the change in energy of the system, which for a closed stationary system is basically change in internal energy of the system. Is it clear so far?
Yes, sir.
All right, great. Again, for a closed system, this term, that means this portion of your equation would essentially be zero. So you'll have only Q in, Q out, work in, work out. That would contribute towards the total energy of a stationary closed system. Now, this energy interaction could be in various forms. It could be in the simpler form, which is heat flowing into the system or heat flowing out of the system, work flowing into the system or work flowing out of the system. At times, you represent this generic form of the equation, which says E in minus E out comprise heat, work, and mass energy interaction, and change in total energy of the system is basically change in internal energy, kinetic, and potential energies of the system. This is the simplest form. At times, your data is given such that you are dealing with a rate of heat flowing into the system, a rate of work done on the system or by the system, and mass, and the rate at which mass flows into the system or moves out of the system. This would be equivalent to the rate at which the internal energy of the system is changing, or the rate at which the kinetic energy or potential energy is changing. So we have expressed in form of rate also. The same equation we have also expressed with regards to time. Why? Because at times you are given the data, that means that is let's say the the power of the bulb that is lighting the system is, let's say, 12 watt. So the power that is coming into system basically would be expressed in E dot in. All right. So at times you have to use this form of the equation, which is essentially the same equation, but it is expressed with regards to time. Same equation would have, this rate equation would have the components expressed in this form, where Q, that is the total heat into the system, is basically the rate at which heat is flowing into the system multiplied by the time for which it is flowing into the system. Similarly, the work, the rate of work done multiplied by the time for which it is being done. And similarly, the change in energy of the system is basically the change with regard to time multiplied by the time for which that change took place in the system. Moving on, you can also express the same equation in terms of per unit mass or specific form. That is, energy per unit mass flowing into the system minus energy per unit mass flowing out of the system is equivalent to the energy change of the system per unit mass. Clear enough?
Yes, sir.
Okay. And then there is another form which is the differential form. That means differential amount of energy moving into system minus differential amount of energy flowing out of system is equal to differential amount of change in energy of the system. Now, if you see over here, I have inexact differentials over here, and I have an exact differential over here. Can somebody tell me why is that? Anybody could tell me why I have expressed inexact differentials with the energy flowing in and flowing out, while I have used exact differential for change in energy of the system?
सर आई थिंक वो डिटेल्स ऑफ प्रोसेस पे डिपेंड नहीं करता ना, तो इसी वजह से हम partial
Yes, if you see change in energy of the system, it is energy 2 minus energy 1. Essentially, it is dependent upon the states. So if the states are fixed, the change in energy of the system would be fixed no matter how you do that. Whereas inexact differentials are used because you are expressing heat and work which are not state functions. Heat and work or even mass flow are not state functions. All right. So that's why you have used inexact differentials with heat and work, which are not dependent upon the states, which have no meaning on state for a specific state. They are process dependent. And the energy at state 2 minus state 1, total energy of the system is basically dependent upon the state of the system. That's why exact differentials have been used with change in energy of the system. So far, is it clear? Is it clear so far?
सर वो जो
Yes,
ऊपर
sir.
आपने ई मैस माइनस ई मैस आउट उसको जीरो किया था वो क्लोज सिस्टम की वजह से किया था
G, this is for the closed system. If the system is closed, there would be no mass flowing in, no mass flowing out. So this portion would be essentially zero. Clear?
ठीक है सर
All right. Now, let's say I have, you already know how do you define the state? You define by two independent intensive properties. So let's say I have a state at this point. This is my state one. If my system moves from state one in this direction and then finally comes back to the same state, my system comes back to the same state, what would be the change in energy of the system?
Zero, sir.
Very good. Why? Because and total energy is dependent upon the state. So if I move from one state and come back to the same state, the total energy of the system would remain same. So there would not be any change. Clear?
यस
Is it clear?
यस सर
All right, great. So if I look, and this process is basically known as cyclic process, where you start from one point and comes back to the same state. It's a cyclic process. For cyclic process, your change in energy of the system is essentially zero. If I write for a cyclic process, which is for closed system, the energy balance equation would be what? Q in minus Q out plus work in minus work out is equal to change in energy of the system. And change in energy of the system would be what for a cyclic process?
zero
Zero, sir.
It would be zero. So if I could write it in this form, that Q in minus Q out is equal to, if I take these two terms, the work terms on the other side of the equation, it would be work out minus work in. Is it clear?
Yes, sir.
All right, I can write this expression which says Q in minus Q out as Q net into the system is equals to work net out of the system. Clear? Is this point clear?
Yes, sir.
Can you confirm me whether this point is clear or not?
Clear.
I cannot hear you. Can someone confirm me
एक
whether the
बार
point is
एक
clear?
बार एक
जी?
बार फिर से इसे
Clear.
एक बार फिर से समझा दें.
This point, ये equation आपको clear है? Q in minus Q out equals to work out minus work in. Is this equation clear to you?
Yes, sir.
So what I am writing is basically in दोनों का difference जो है I am expressing it with Q net, and I am writing it with positive sign, and I am writing in over here. यहाँ पे मैं in लिख रहा हूँ और positive sign express कर रहा हूँ क्योंकि मेरे पास यहाँ पे in के साथ positive sign है. Is it clear? So I am writing the difference is basically Q net, and since I am writing it with positive sign, I would write Q net in. All right.
Yes, sir.
Similarly, I am writing the difference of work out minus work in as work net, and I am writing out in the subscript since this is positive sign over here and work out also has positive sign over here. Is the point clear to you?
Yes, sir.
Anybody who has doubt?
सर ये जो आप क्लोज सिस्टम है, मतलब कि अगर हम कोई भी क्लोज सिस्टम लेंगे तो उसमें जो स्टेट है वो कभी चेंज नहीं होगी.
If I am talking about a cyclic process, this is all about a closed system which is undergoing a cyclic process. Cyclic process means that it started from state 1 and came back to state 1. For that system, the change in energy of the system would be essentially zero. अगर और कोई प्रोसेस होगा स्टेट 1 से स्टेट 2 पे जाएगा, so there would be some change in energy of the system. If your system moves from state 1 to state 2, then there would be state change in energy of the system. The change in energy of the system would not be zero in that case. Clear?
Clear, sir.
I hope the point is clear to you why I am writing Q net in and work net out. I hope this is clear to you.
Yes, sir.
Yes, sir.
All right. So I'll clear the slide and I would again show you that for a cyclic process, Q net is equal to work net. And I normally express this in terms of work net out equals to Q net in. Why? Because in the equation, if I move work net out on one side and keep it positive, work net is basically expressing the difference between the two works. Out is basically used because you are using a positive sign. Similarly, in is used because uh, Q in would have a positive sign if you write Q terms on one side of the equation and W terms on the other side of the equation. Clear enough?
Yes, sir.
All right. So this again, work net out and work Q net in is expressed in terms of rate, where you have dot on top of both the heat energy transfer mechanisms. Moving on, we'll quickly go through an example to see, since we have been through equations, too much equations, we'll see how to apply these equations. So I'll do one example today and the remaining example in the upcoming class. So kindly have your notebooks with you in the upcoming class because we'll start from the examples of energy balance equations. We'll start with one example today and we'll continue with the examples in the upcoming class. All right. So the example says that you have a rigid tank which contains hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. During this cooling process, the fluid loses heat of 500 kilojoules, and the paddle wheel performs work of 100 kilojoules on the fluid. Determine the final internal energy of the fluid. The first thing that you need to do is draw a schematic so that it becomes easier for you to apply the energy balance equation. Schematic is very important. So if I have this rigid tank and there is some fluid inside it, the information given to me is that the internal energy U1 at state 1 is 800 kilojoules. This is the first information given to me. Moreover, it is given to me that the system loses heat in the form of 500 kilojoules. So Q out of the system is essentially 500 kilojoules. Clear? And then there is a paddle wheel which is being attached to the system, and it is being rotated so that the work it performs into the system is work into the system, which is essentially 100 kilojoules. Clear enough? Is this point, is the equation, is the system clear to you?
Yes, sir.
You have to find the internal energy of the system at state 2. This is what you have to find out. So these are the energy interactions taking place, and internal energy U1 and U2 is basically representing the change in energy of the system. What we have to do is that we neglect the energy stored in the paddle wheel. That means whatever energy this shaft is being rotated, all of that energy is delivered to the system. It is not consumed by the paddle wheel. All right. This is our assumption, which is given in the question. So you have the system with you over here again, where shaft work coming into the system is 100 kilojoules, heat going out is 500 kilojoules. Initially, the system is at internal energy of 800 kilojoules. What is the final internal energy of the system? How do? You move on with the assumptions. Once you have drawn the schematic, you move on with the assumptions. Assumption says that the tank is stationary. And if the tank is stationary, the kinetic energy change and potential energy change would be zero. So the total change in energy of the system would essentially be equivalent to the change in internal energy of the system. Is this clear?
Yes, sir.
All right. And the second assumption which is given to you is that paddle wheel doesn't store any energy. That means all of this amount of energy is being delivered to the system. It is not consumed by the paddle wheel. Clear?
Yes, sir.
All right. Now, if I look at the details that we have discussed so far, we have taken the contents of the tank as the system. And since it's a rigid tank, we have assumed it to be a closed system, that no mass is crossing the boundary during this process. Since the volume of the tank is constant, there is no moving boundary work that is being done on the process. Heat is being lost to the surroundings, and shaft work is done on the system. With this, we apply the energy balance on the equation, energy balance equation on the system, and we say that energy coming into the system minus energy going out of the system is equal to the change in energy of the system. So what is the energy coming into the system? It is essentially work in that is coming into the system. Is there any heat coming into the system?
No, sir.
So Q in would be 0. Should there be any mass coming into the system?
No, sir.
So the only energy that is coming into the system is basically work in. And what is going out of the system? Q out is basically going out of the system. And that would be equivalent to change in energy of the system, which is essentially equal to change in internal energy of the system. So if we apply the equation, or if we elaborate on the equation, we see that we have shaft work in coming to the system, heat moving out of the system, and the change in the internal energy of the system is U2 minus 1. Now, if you see, this value is given to you, this value is given to you, initial state internal energy is given to you. The only thing unknown is basically the final internal energy of the system. If you plug in the values, you would find out that the final internal energy of the system is 400 kilojoules. Clear?
Yes, sir.
Stop over here, and we'll continue from the energy balance equation examples in our upcoming week.